Light enters air from water. So how does the angle of refraction compare to the angle of incidence? First of all, make sure that you read this correctly when you draw your interface. Let's say that you have air here and water here. Make sure you have it entering air from the water, so it's coming from the water. So if you draw your normal to the surface, the incident angle is coming from the water and it's going to refract into the air. So this right here is the angle of incidence, and it's refracting into the air. It travels faster in air. So we have this little tool here to help us remember FST SFA. When it's going from a slow medium like water to a fast medium like air, the light refracts away from the normal, so it's going to refract away. So this will be the angle of refraction, which is greater than the angle of incidence. Number 2. This one, you had to put a little bit of thought into it here. You have the ray of light is in glass, is incident on a plane glass air boundary, and gives us the index of refraction, and we want to know what happens to this ray. Alright, so it's going from the glass to the air, so it's going from a high index to a low index. So N1 is the starting index, is the glass, is the 1.5, and it's going into air. So N2 is 1. Alright, so again, if you picture this, we can draw it just like the one above. We're going from glass, and we want to know what happens. Well, when you go from a high index, N1, to a low index, N2, if your angle of incidence right here, this is my angle of incidence, if it's high enough, if it's greater than the critical angle, then all of the light will be totally internally reflected. So the first thing you can do when you're going from a high index to a low index is see what is my critical angle. So the critical angle is given by sine of the critical angle is equal to N2 over N1. So when you go ahead and solve this for the critical angle by taking the inverse sine, you're going to get a critical angle of 41.8 degrees. So that's the critical angle. If light is incident at that critical angle, then it will be refracted at 90 degrees. It will be refracted here along the surface. If the angle of incidence is any greater than this, that means all of it will be totally internally reflected, and it's going to go back this way. So the angle of incidence of 45 is greater than the critical angle, so we're going to have total internal reflection, which was choice B. Number 3, so white light disperses through a prism. Which color moves the lowest? So that's going to be the blue. We learned that the index of refraction for blue light is higher. So if n is higher and n is defined as c over v, then n being a higher number means that the speed is lower. So blue moves the slowest and red moves the fastest. We also learned that blue ends up being bent the most, while red ends up being bent the least. Number 4, so monochromatic light hits a piece of glass. What happens to the wavelength in the glass as the index of refraction increases? So the index of refraction is related to the wavelength of the light in vacuum divided by the wavelength of the light in the medium. So if we just solve this equation for the wavelength of light in the medium, which is glass, we get that it's equal to the wavelength in vacuum divided by n. So we can see that if we increase the index of refraction, then the wavelength in the glass gets smaller.